Firewall computing.
In computing, a firewall is a software or hardware-based network security system that controls the incoming and outgoing network traffic based on applied rule set. A firewall establishes a barrier between a trusted, secure internal network and another network that is not assumed to be secure and trusted. Many personal computer operating systems include software-based firewalls to protect against threats from the public Internet. Many routers that pass data between networks contain firewall components and, conversely, many firewalls can perform basic routing functions.
History.
The term firewall originally referred to a wall intended to confine a fire or potential fire within a building. Later users refer to similar structures, such as the metal sheet separating the engine compartment of a vehicle or aircraft from the passenger compartment. Firewall technology emerged in the late 1980s when the Internet was a fairly new technology in terms of its global use and connectivity. The predecessors to firewalls for network security were the routers used in the late 1980s. Clifford Stoll's discovery of German spies tampering with his system, Bill Chesik's Evening with Burford 1992, in which he set up a simple electronic jail to observe an attacker. In 1988, an employee at the NASA Ames Research Center in California sent a memo by email to his colleagues that read, "We are currently under attack from an Internet virus. It has hit Berkeley, UC San Diego, Lawrence Livermore, Stanford, and NASA Ames." The Morris worm spread itself through multiple vulnerabilities in the machines of the time. Although it was not malicious in intent, the Morris worm was the first large-scale attack on Internet security. The online community was neither expecting an attack nor prepared to deal with one.
First-generation packet filters.
The first paper published on firewall technology was in 1988, when engineers from Digital Equipment Corporation, DEC, developed filter systems known as packet filter firewalls. This fairly basic system was the first generation of what is now a highly involved and technical Internet security feature. At AT&T Bell Labs, Bill Chesik and Steve Bellavin were continuing their research in packet filtering and developed a working model for their own company based on their original first-generation architecture. Packet filters act by inspecting the packets, which are transferred between computers on the Internet. If a packet matches the packet filter's set of filtering rules, the packet filter will drop, silently discard the packet or reject it, discard it, and send error responses to the source. This type of packet filtering pays no attention to whether a packet is part of an existing stream of traffic, that is, it stores no information on connection state. Instead, it filters each packet based only on information contained in the packet itself, most commonly using a combination of the packet's source and destination address, its protocol, and, for TCP and UDP traffic, the port number. TCP and UDP protocols constitute most communication over the Internet, and because TCP and UDP traffic by convention uses well-known ports for particular types of traffic, a stateless packet filter can distinguish between, and thus control, those types of the traffic, such as web browsing, remote printing, email transmission, file transfer, unless the machines on each side of the packet filter are both using the same non-standard ports. Packet filtering firewalls work mainly on the first three layers of the OSI reference model, which means most of the work is done between the network and physical layers, with a little bit of peeking into the transport layer to figure out source and destination port numbers. When a packet originates from the sender and filters through a firewall, the device checks for matches to any of the packet filtering rules that are configured in the firewall and drops or rejects the packet accordingly. When the packet passes through the firewall, it filters the packet on a protocol port number basis, GSS. For example, if a rule in the firewall exists to block telnet access, then the firewall will block the TCP protocol for port number 23.
Second generation, stateful filters.
From 1989 to 1993, colleagues from AT&T Bell Laboratories, Dave Presetto, Janardhan Sharma, and Kshitij Nigam, developed the second generation of firewalls, calling them circuit-level gateways. Second-generation firewalls perform the work of their first-generation predecessors but operate up to Layer 4, transport layer, of the OSI model. This is achieved by retaining packets until enough information is available to make a judgment about our state. Known as stateful packet inspection, it records all connections passing through it and determines whether a packet is the start of a new connection, a part of an existing connection, or not part of any connection. Though static rules are still used, these rules can now contain connection state as one of their test criteria. Certain denial-of-service attacks bombard the firewall with thousands of fake connection packets in an attempt to overwhelm it by filling its connection state memory.
Third generation, application layer.
Marcus Ranum, Weizhou, and Peter Churchyard developed an application firewall known as Firewall Toolkit, FWTK. In June 1994, Weizhou extended the FWTK with the kernel enhancement of IP filter and socket transparent. This was known as the first transparent application firewall, released as a commercial product of Gauntlet Firewall at TIS. Gauntlet Firewall was rated one of the number 1 firewalls during 1995-1998. The key benefit of application layer filtering is that it can understand certain applications and protocols, such as File Transfer Protocol, FTP, Domain Name System, DNS, or Hypertext Transfer Protocol, HTTP. This is useful as it is able to detect if an unwanted protocol is attempting to bypass the firewall on an allowed port, or detect if a protocol is being abused in any harmful way. As of 2012, the so-called Next Generation Firewall, NGFW, is nothing more than the widen, or deepen inspection at application stack. For example, the existing deep packet inspection functionality of modern firewalls can be extended to include intrusion prevention systems, IPS. User identity integration, by binding user IDs to IP or MAC addresses for reputation. And Web Application Firewall, WAF. WAF attacks may be implemented in the tool WAF fingerprinting utilizing timing side channels, WAFL.
Types.
There are different types of firewalls depending on where the communication is taking place, where the communication is intercepted and the state that is being traced.
Network layer or packet filters.
Network layer firewalls, also called packet filters, operate at a relatively low level of the TCP/IP protocol stack, not allowing packets to pass through the firewall unless they match the established rule set. The firewall administrator may define the rules, or default rules may apply. The term packet filter originated in the context of BSD operating systems. Network layer firewalls generally fall into two subcategories, stateful and stateless. Stateful firewalls maintain context about active sessions, and use that state information to speed packet processing. Any existing network connection can be described by several properties, including source and destination IP address, UDP or TCP ports, and the current stage of the connection's lifetime, including session initiation, handshaking, data transfer, or completion connection. If a packet does not match an existing connection, it will be evaluated according to the rule set for new connections. If a packet matches an existing connection based on comparison with the firewall's state table, it will be allowed to pass without further processing. Stateless firewalls require less memory, and can be faster for simple filters that require less time to filter than to look up a session. They may also be necessary for filtering stateless network protocols that have no concept of a session. However, they cannot make more complex decisions based on what stage communications between hosts have reached. Newer firewalls can filter traffic based on many packet attributes like source IP address, source port, destination IP address or port, destination service like www or FTP. They can filter based on protocols, TTL values, net block of originator, of the source, and many other attributes. Commonly used packet filters on various versions of Unix are upfilter, various, IPFW, FreeBSD, Mac OS X, NPF, NetBSD, PF, OpenBSD, and some other BSDs, Iptable zip chains, Linux.
Application layer.
Application layer firewalls work on the application level of the TCP/IP stack, that is, all browser traffic, or all telnet or FTP traffic, and may intercept all packets traveling to or from an application. They block other packets, usually dropping them without acknowledgement to the sender. On inspecting all packets for improper content, firewalls can restrict or prevent outright the spread of networked computer worms and trojans. The additional inspection criteria can add extra latency to the forwarding of packets to their destination. Application firewalls function by determining whether a process should accept any given connection. Application firewalls accomplish their function by hooking into socket calls to filter the connections between the application layer and the lower layers of the OSI model. Application firewalls that hook into socket calls are also referred to as socket filters. Application firewalls work much like a packet filter, but application filters apply filtering rules, allow block, on a per-process basis instead of filtering connections on a per-port basis. Generally, prompts are used to define rules for processes that have not yet received a connection. It is rare to find application firewalls not combined or used in conjunction with a packet filter. Also, application firewalls further filter connections by examining the process ID of data packets against a rule set for the local process involved in the data transmission. The extent of the filtering that occurs is defined by the provided rule set. Given the variety of software that exists, application firewalls only have more complex rule sets for the standard services, such as sharing services. These per-process rule sets have limited efficacy in filtering every possible association that may occur with other processes. Also, these per-process rule sets cannot defend against modification of the process via exploitation, such as memory corruption exploits. Because of these limitations, application firewalls are beginning to be supplanted by a new generation of application firewalls that rely on mandatory access control, MAC, also referred to as sandboxing, to protect vulnerable services.
Proxies.
A proxy server, running either on dedicated hardware or as software on a general-purpose machine, may act as a firewall by responding to input packets, connection requests, for example, in the manner of an application, while blocking other packets. A proxy server is a gateway from one network to another for a specific network application, in the sense that it functions as a proxy on behalf of the network user. Proxies make tampering with an internal system from the external network more difficult, and misuse of one internal system would not necessarily cause a security breach exploitable from outside the firewall, as long as the application proxy remains intact and properly configured. Conversely, intruders may hijack a publicly reachable system and use it as a proxy for their own purposes. The proxy then masquerades as that system to other internal machines. While use of internal address spaces enhances security, crackers may still employ methods such as IP spoofing to attempt to pass packets to a target network.
Network address translation.
Firewalls often have network address translation NAT functionality, and the hosts protected behind a firewall commonly have addresses in the private address range, as defined in RFC 1918. Firewalls often have such functionality to hide the true address of protected hosts. Originally, the NAT function was developed to address the limited number of IPv4 routable addresses that could be used or assigned to companies or individuals, as well as reduce both the amount and therefore cost of obtaining enough public addresses for every computer in an organization. Hiding the addresses of protected devices has become an increasingly important defense against network reconnaissance.